Covariance. How much do you know about it? It has confused programmers forever, and I know why. Covariance is great in collections, but collections are precisely what cannot be covariant in C#. If you ever had a chance to truly use covariance, you would love it. That is the easy part. The hard part goes beyond anything C# collections can do today. Still, there is one secret technique known to very few that defines collections that are truly covariant. Am I talking in riddles? Alright, time to start coding. Nothing explains theory better than code. I start with an abstract record called animal, the base type for everything our collections will hold. 3 concrete animals derive from it: giraffe, elephant, and lion. A small but complete hierarchy. I add a property to the giraffe type, something concrete to use in a collection of giraffes. Then comes the collection. Covariance is best observed on collections, so the array of giraffes it will be. Fill the array with 3 giraffes of various neck lengths, the data I want in a moment. How do we print giraffe neck lengths then? That is where it gets interesting. Since the array only contains giraffe objects, we can measure each animal's neck and print it. Business as usual, nothing special. Wait no longer, this is where the trap opens. We can assign the giraffe array to an animal array variable, and the compiler says nothing. Arrays are covariant in C#. A derived array is assignable to a base array, but that assignment has always been broken. Before breaking this code, let me show what works. We can print the animals array because all animals have toString implementations, but we cannot access the neck length property. The array is declared as animals and only giraffe has neck length. This does not compile and the type system is right. Let me fix the error and run the demo before I break it. Let's see what the application prints. Here is the output. Both loops access the same objects only through a different declared type. And here is the problem. The animals array is mutable and declared as animal, so why not put an elephant there? The compiler has no objection, but the array is really giraffes, and the CLR knows it. What happens when I run the application again? Oh, an unhandled exception, array type mismatch exception. The message says, attempted to access an element as a type incompatible with the array. Well, yes, that is precisely what I did. I'm guilty as charged. C# defines arrays as covariant, but not entirely. You can assign a derived array to a base array, but you cannot store elements that do not derive from the original type. That was a mouthful, sorry. That's what you get when you start analyzing covariance. Would a list be any better than the array? The assignment to the animal array is still there and now it fails. A generic list is not assignable to an array, whatever the element types. Even assigning to a list of animal fails to compile. You could add an element into a list that is really giraffes. How would console write-line print the neck length of an elephant? That is not covariance, that is a ticking bomb. Mutable collections in C# cannot be covariant because that opens the door to unexpected types and runtime errors. But wait, why use a collection at all? Why not a read-only sequence? The compiler accepts this because IEnumerable has no way to accept new elements. Covariance is safe exactly when the type cannot be written to. I wasn't writing to the giraffes collection either, so it can be a read-only sequence too. The assignment below compiles because the generic IEnumerable is defined as covariant. Still, we need to add elements, as I tried with the array squeezing an elephant into it. I will therefore create a proper covariant list of my own. The interface is empty, and I must think carefully about what goes inside. Compile time errors from the consuming code will tell me what my ingenious covariant list is missing. First off, I cannot populate a list without a concrete implementation. That comes soon, so I postpone this operation. The next requirement is iteration. My list must implement IEnumerable, which immediately puts a link on the table. So far so good, but covariant assignment to a list of animals still fails. That is where covariance steps in. The out modifier says an list will only return objects of type T, never accept them on input. That has profound consequences on how lists are assigned. The warning is about possible null assignment, not type mismatch, and I will fix it later. My goal now is to explain what out really does. Here is the key insight. We know that giraffe derives from animal, but when list declares its type parameter as out, a list of giraffe behaves as if it derived from a list of animal. That second relationship between the two list types is what out grants us, and such a generic type is called covariant. Simples. Now the troubles begin. The requirement is to add new items into the list. Would the compiler allow this method? No. The error is invalid variance. T is out, so it can only appear in output positions, but add consumes a T, an input position, which is contravariant. Declaring T as both in and out? The compiler refuses that too. A type parameter is in or out, never both. That flat dismisses any possibility of defining an add method on the list. That also explains why none of the collections in C# is covariant. They simply cannot be covariant, unless you know a secret technique, which I am about to show you now. But before that, let me steal a moment of your time to remind you that all the videos here are free, but only thanks to the people who support this channel. If you like what you are learning from my videos, then please consider joining the growing community of patrons on my Patreon page. That is the only way for the content on this channel to stay free for everyone. Thank you very much for your support. Now let's get back to code, where I have a neat surprise for you. We can define add as an extension method. Here is the trick. An input reference is always contravariant, as object substitution works in any object-oriented language. Defining a contravariant method as an extension is the loophole, and a beautiful one. Add receives T as an input argument, and yet list stays covariant. How to implement it comes later. You should worry about a different problem. How can we add an elephant to a list created for giraffes? That is the array problem again, where .NET threw an exception to protect itself. Here comes the second half of the idea. For the type to remain covariant, it must be immutable. A contravariant extension returns a fresh instance, leaving the original giraffe list untouched. Adding an elephant to an animal list produces a new animal list, not a giraffe list with an elephant. The rest is regular, everyday, normal work. A static empty property is a common way to initialize immutable collections. Once I implement the concrete types, the rest works like a charm. I can fill the gaps starting from an empty list of giraffes. Then add items one after another, each time obtaining a new immutable covariant list. There will never be any null references here. I can remove the null forgiving operators. Covariant assignment of a giraffe list to an animal list is now perfectly legal. If you still struggle to see it, wait 1 minute longer. We need concrete implementations of list. That is where the design falls into place. The first concrete type is the empty list. Immutable design commonly solves trivial cases with dedicated classes. That keeps the general case easier, as you will see. The empty list is enough to complete the empty static property. That leaves the ultimate piece of the puzzle, the general covariant list. The true immutable list in .NET takes hundreds of lines, mostly for performance. Here I show only the working principle. The list is an existing list concatenated with a single new element. The existing list can be empty, which is why I implemented it first. We need the means to enumerate the elements. Recursively untangle all elements from the previous list, then add the last one at the end. Performance will be terrible, but my plan is only to show the principle behind a true covariant type. So far, I have succeeded in that endeavor completely. Look at the hardest piece, the add method. It boils down to instantiating a new concatenated list. Such is functional design. Most methods are one-liners that combine other concepts to produce the result. Nevertheless, the demo is now fully operational. We can create and populate the covariant list of giraffes. We can iterate through its elements and access strongly typed giraffe objects. And here is the covariant assignment, where a base type list is the base of a derived type list. That is covariance by definition. Only the hardest operation is missing. I call add on the animal list, passing a new elephant. This blew up with arrays, but now it is safe. The giraffe list stays intact, and a new animal list holds the elephant. Let's see the printout. There it is. The giraffe array remained intact, still holding only giraffes. But the next version is a list of animals, freely accommodating giraffes, elephants, and whatnot else. The bottom line is that I have successfully implemented a fully covariant list implementation based on immutable design and contravariant operations implemented as extension methods. That is one of the most beautiful techniques you will ever find in C#. And provided that you have paid attention to everything I said in this video so far, the technique that will give you a whole new perspective on the entire object-oriented programming.